Hello and welcome to my channel. Happy Thursday. Hope everyone's doing well. I'm Professor L, and this is a live stream for Math Help. So if you want to participate, you're welcome to post problems in my chat, and I'll either work it today if I can or next time. And so I'm going to go ahead and get right into what I was going to present today. I am in trigonometry subject right now, and we are going to be calculating the vertical and horizontal components of a force vector that is acting on an incline. So I'll go ahead and just get right into it. I got some fresh markers, so hopefully this will be short and sweet. It seems like that's the way we like it in the 21st century. And so we're talking about these force vectors, and what a force vector is. The object in geometry that would best represent it would be a directed line segment. I guess it would be called a ray, where it has a point on one end and then it's got an arrow on the other. And vectors in particular are directed line segments where they have a specific direction according to the compass, north, south, east, and west, and it has a magnitude. And the magnitude is directly proportional to the length of your vector. And you usually will you'll set a scale, because a lot of times your drawings are representing real vectors and situations in real life that obviously have to have a scale drawn so that they can be shrunk. So this is a right triangle trigonometry problem involving a force vectors acting on an incline. So force. Can I even spell force? Vectors, I guess I can. All right, so here is what's going on. And again, when you're solving these applications problems, you really want to get an accurate sketch, and there is a method to it. So what this problem is asking is specific directions. It says find horizontal and vertical components of the force. And I did number 1 to practice. It was given to me in the back of the book. So let's do this next one just for it, so it can be fun for me too. So it's 2,183 pounds. So let's go ahead and put the directions up here. Find horizontal and vertical components of the force. And it says 2,183 pounds acting downward. At an inclination of 36 degrees and 33 minutes. What did I say? I already forgot. 36, 33. Sorry. And 33 minutes. Okay, there we go. Right. So what we need to do first thing is to go ahead and get an accurate sketch. So let's see where we're going to put it. And so what we're doing, what I want to explain kind of, because it does get confusing, we're going to go ahead and put our Cartesian coordinate system up here, and I'll show you what's going on here. So we'll start out with this kind of thing. And say we have, there's our origin, and we'll have a vector here. So we have, so the force, this is the magnitude of V, and we could call this component, this is north, south, east, west. And so this component is the y-axis, and this is the x-axis. And so this is going to be the well, this will be the horizontal component, and this is going to be the vertical component. And so for what's going on here is you have obviously the y-axis is so you have y equals sine x, or sine theta rather, we'll use theta. And then you have x equals cosine theta. So we have we have the vertical and the horizontal component here. But what happens is, so you have, let's go ahead and name these vectors here. This would be f sub y, and then this one would be f sub x. For your vectors here, the components. When you have an incline, so the incline is in respect to your horizontal. Okay, and if you're having an incline that's acting on an angle here, and it says 36 degrees, 33 minutes. Let's go ahead and change that to a decimal real quick, so I don't have to go back and forth. I can just change it back all at once. All right, 36.55 degrees. We'll call this angle theta, and theta equal 36.55 degrees. If you could imagine that this is shifted, it's shifted so that north is going to be equivalent with the incline. So north is this direction now. It's still straight up, but what happens when you're having an incline, that this becomes this the horizontal component. Okay, so rather than, and then so then x becomes the vertical component. So you have f of x is going to be the cosine. So it's going to be opposites, and that's the reason why. So you have f of x is, so it's the magnitude of v times the cosine of theta, and then you have f of f sub y, so it's going to be your horizontal component is the absolute value of v sine theta. And I hope I did a decent enough job of explaining why in the incline, the horizontal component becomes the sine. Because here, if it was just on the x-axis and you had this thing, it would actually be the vertical component. So it is flipped for the incline. And this is something that, again, I'm not a physics expert. The only, the strong point for me would be the trigonometry, but yeah, it's nice to get into these applications, and so that's why I'm here. All right, so it's just important to note that. So when you're calculating your components, you don't get them flipped. I made that mistake once. And let's see where we're at. And then also what I'll do is, since this is the one that's not in the back of the book, I'll plug it in to the computer. I should have done that before actually, but I didn't think about it. All right, so what we can do, all we're doing is plugging into this form to find these values. Let's kind of draw a picture of what's going on. So the horizontal, it could be a ramp or something. And it's quite a bit of weight because let's see, like a vehicle, what is that, a couple of tons? And wait, a ton is 2,000. So it could be about the weight of a car, like driving up the ramp. So the force is pulling the car. Let's see if I can draw a decent car here. The tires. I at one point in time liked to draw quite a bit, and if I can just get some sort of car here. Maybe it's a speedster. It's got a door. Not too bad. Windshield wipers. Antenna. Anyway, so we might have a car, and the force is, it says acting downward at an inclination here of theta. So the force is going this direction. So in order to find that horizontal component, we're looking at for a force that's equal and opposite in direction that is going to hold it. So it says this way, so it's wanting, all it's wanting is these horizontal vertical components. So what we're going to do is we're going to draw, and let me get rid of theta and make it smaller because I think that I need to draw this a little bit bigger, honestly. And this is like, me getting some drawing skills here. But it's important to see a big picture. When I was taking physics class, I remember the teacher getting frustrated with me because I remember him telling me distinctly, and I tend to be kind of stubborn, but he was like, no, then it's directly down. Because whenever I was drawing these, when I was first learning, I would want to put the Newton force this way, which is because I'm used to the Newton force being perpendicular to the line of motion. And gravity goes straight down. And so even though you're on an incline, you've still got that gravity, that Newton. And that is the actual weight of the object that is it's mass times the acceleration of gravity. It's the weight of the object, which is this right here. So this point right here, this ray represents this 2,183 pounds right here. 2,183. But what's happening is so now it has a force that's perpendicular to the line of motion. And this is your vertical component, which will be, see, now I got it switched. It's going to be your cosine. This is your vertical. And then this one will be your horizontal. And I said that with a lot of authority, but now I'm not sure. I'm going to go make sure. All right, so I had the thing pulled up, so let me see. Does that one say, okay, F of V is sine. And so that I'm pretty sure now I thought I had it. All right. A's. Okay. All right. So then what we have is our Newton. Now this is going to be our vertical component here. So this is going to label it F sub X. And then we're going to label this one here. This one's going to be F sub Y. So we've got vertical and horizontal. All right. So all we have to do is plug in the form. So we've got the magnitude. So we'll just plug that in and make a list. It's 2,183. And then theta was 36.55. So we're going to say 2,183 times the cosine of 36.55. And then the magnitude times the sine. Let's see, 2,183 times the sine of 36.55. And let's see what's going on here. Let's go ahead and plug in our calculator. Let's see what we got. And then I'm probably going to go ahead and plug it into this, the computer to see if it'll tell me the correct, make sure I got the right answer. 2,183 cosine 36.55 is, I got 1753. So 1753.685705. And real quick, the sine. Yeah, I got 1,300. And 0.29018. All right, so let's go ahead. All right, let's see what it says. All right, I got it right. Yay. Okay, it says that 1,303, so 1,300.03 pounds parallel to the incline. And 1,753.69 pounds perpendicular to the incline. All right, so we've got it correct. What's happening is what the difference in these components is, they're actually forces that are acting on the object simultaneously at the same time. So when you have a car and it's on the incline and maybe you have a brake, maybe you have it stopped and it has its brake, it still has that force pulling on it. And the brake has to be equal and opposite in order to stop that vehicle from rolling down the hill. And so this horizontal component here, the sign, what it's doing is it's representing the force of the vehicle, that the force that's pulling on that vehicle that's wanting it to roll down the hill, that if it didn't have a brake, it would just take off and roll down the hill with this magnitude. This is the magnitude. That's acting on the object. This force right here, this perpendicular force, is it's the physical weight of the vehicle, like parked on, like it's got the Newton force acting on it. Like right now, I'm standing with a vertical orientation against the earth in a perpendicular, at a perpendicular angle. And so we stand at perfect perpendicular. And if we try to lean off, we'll fall off of balance pretty quick. Well, it's kind of the same thing. I have a particular weight. I haven't weighed myself in a while, but it's my actual mass times the force of gravity acting on it. It's 9.8 meters per second. And or it's meters per second. Anyway, yeah, not a physics expert, but I do enjoy the applications of the physics. But I just want to kind of explain what's going on, because these are individual forces acting on this object. So we've got the weight of the vehicle on the actual, what it's surfaced on, and then we have the weight of gravity also pulling that vehicle. So the weight of the gravity that's pulling the vehicle doesn't have to be as strong because of the incline. And that's probably, I don't want to get off into theory, into the weeds too much, because I really don't know for sure, but it is good to speculate on things. And so, yeah, I would venture to say that that's the reason why these values are flipped, because really, if you notice, like in this orientation, the y is clearly perpendicular to, well, I guess they're perpendicular to each other, but this one looks more perpendicular to the horizontal as far as the orientation. So it's interesting that it would shift on an incline and the horizontal would become the y-axis, because here the horizontal is represented the f. So I kind of lost my live stream, so I need to get the picture back here and make sure that we're still going. And see where we're at. That was a really short live stream for today, but I don't mind having a light day. I try to keep it about, especially if I don't have problems to work for actual like students, like I would rather keep it practical. And so yeah, I will go ahead and probably stop there for today. And I am going to go ahead and have one tomorrow, another live stream. And so we'll see what I decided to talk about tomorrow. I do want to stay in applications of right triangle trigonometry for right now. And eventually maybe possibly get into some different, if it's not right triangles, you can still use trig. There's laws of sines and laws of cosines. And I realized with the parallelogram method for that problem I worked yesterday, whenever you're finding the resultant of two vectors, you're adding vectors. you can add them and geometrically find that resultant vector using a parallelogram. And there's two methods of finding it geometrically. There's a parallelogram method, and then there's that head. It's like the head tail method, where you put the beginning of one vector and the tail of the other one, and then anyway, there's a way to find the resultant that way too, but you have to have really accurate sketches. So I would have to probably set a scale and get a ruler. So I'm feeling like I'm not going to be able to show those until I explain and talk about laws of cosines and laws of sines. So what I'll do is I'm going to for now stay with right triangles. So that's what to kind of expect. And I'll go ahead and sign off for today. We'll manage to talk for a whole 25 minutes, 26 minutes. And so, yeah, I will see you again tomorrow, same time, same place, and hopefully I will find something that's useful. For now, I will see you next time. Bye.